This is an example for a torsion pendulum. So we have the figure below shows a thin rod whose length L is 12.4 centimeters, which of course is 0.124 meters, and whose mass M is 135 grams or 0.135 kilograms. And it's suspended at its midpoint from a long wire. Its period of angular simple harmonic motion is measured to be 2.53 seconds. So that's our period, and I'll call this the rod. Period of the rod is 2.53 seconds. An irregularly shaped object, which we call object X, is then hung from the same wire as the figure below shows, and its period TB is found to be 4.76 seconds. So I'm going to call this period of object X is 4.76 seconds. And then what is the rotational inertia of object X about its suspension axis? So rotational inertia I of object X is equal to question mark. So this is similar to when we have like a mass on a spring or something like that. Think of our torsion constant. So here we have a torsion pendulum, and it's hung from a suspension wire that has a torsion constant. So you think of the torsion constant kind of like a spring constant K. And so since it's the same suspension wire, it will have the same torsion constant. So the key here is that we need to find the torsion constant from the information given about the rod first. And then because object X is hung from the same wire, it will have the same torsion constant, and then we can find our rotational inertia from that. Because we know that when we have a torsion pendulum, that our period is equal to 2 pi times the square root of our rotational inertia I over the torsion constant kappa. Okay, so we know that we can find rotational inertia of the rod because we have the mass and the length. We have the period T for the rod as well, so we can find torsion constant from that and then use it in a second equation using period in order to find our rotational inertia for object X. So if I solve this equation for my torsion constant K, I am going to divide both sides by 2 pi, and then I'm going to square everything so to get rid of that square root. So I'll end up getting T squared over 4 pi squared equals rotational inertia over torsion constant. And then cross multiply and divide by T squared or period squared. So we get torsion constant is equal to 4 pi squared times the rotational inertia divided by T squared. Now we're talking about a rod here, and it is being rotated about a central axis. So the rotational inertia for that is going to be 1/12 ml squared. So plugging that in here, we get 4 pi squared times 1/12 ml squared divided by period squared. So plugging our numbers in for the torsion constant, we get 4 times pi squared times 1/12 times the mass of the rod, which was 0.135 kilograms, times L, the length of the rod, 0.124 meters. And I'm going to square that, and then all divided by the period for the rod, which was 2.53 seconds squared. So plugging everything in, we get 4 times pi squared times 1/12 times 0.135 times 0.124 squared, and then all divided by 2.53 squared. And for that, we get about 0.0012. And then the units for K, it looks to be, if we look at our units here, we can see kilograms times meters squared over seconds squared. Not that it really matters that much, but And then now we have our torsion constant. Now remember, since this is the same wire, we'll have the same torsion constant. And so we use the same equation. Period is equal to 2 pi times the square root of rotational inertia divided by torsion constant. But now this is going to be the period of object X and the rotational inertia of object X. So here we're solving for rotational inertia. So I'm going to solve this equation for rotational inertia. So again, dividing by 2 pi and squaring everything will give us period of X squared divided by 4 pi squared equals I X over kappa. And multiply both sides by our torsion constant kappa, and we get the rotational inertia of object X is equal to period of object X squared times kappa divided by 4 pi squared. So now plugging everything in, the period of object X was 4.76 seconds. And then I'm going to square that times kappa, which we just found was 0.0012. Divided by 4 pi squared. So I still have kappa in my calculator, so I'm just going to multiply that now by 4.76 squared, and then divide that number by 4 times pi squared. And I get rotational inertia for object X is equal to 6.123, so about 6.12 times 10 to the negative 4 kilograms times meters squared. And it's hidden. There it is.